Hello friends! In the previous lesson, we set up a basic 3D scene with meshes, materials, a camera, and a light source. In this lesson, we'll accept input from the player. Click on Project in the menu bar and open the project settings. Switch to the Input Map tab at the top of the project settings window. In order to achieve our objective of controlling a 3D character, we need to accept inputs for the 4 movement directions: left, right, forward, and backward. Type Move Left into the Add New Action field, then click Add to add the action. The action name is a description of what the input is used for in our game, conventionally written in lowercase separated by underscores. Actions are triggered by events, which we can add by clicking on the plus button. Events can be keyboard keys, mouse clicks or movement, or input from a joypad. We can search for the desired inputs by expanding their categories, filter the search results, or use the listening field to just press the button we want. For Move Left, most games use the A key or the left stick of a joypad tilted to the left. Adding multiple events will better accommodate different styles of play. We also need to be able to move right, forward, and backward, adding a new action for each. I'll use the D key or left stick right for right, W key or left stick up for forward, and S key or left stick down for backward. The dead zone value is the minimum amount of pressure or tilt required to trigger this action. Now the engine will listen for these input events and trigger these actions. When you're done, click the Close button to close the project settings. Let's create a new node that will react to the input actions we created. This node doesn't need to represent any physical object in our scene, so it can just be a basic node, and name it Player. Anything in our scenes can be given behaviors by attaching scripts to them. Right-click on the player node, select Attach Script, or with the player node selected, click on the Attach Script button in the Scene tab. The default language for scripts in the Godot engine is Godot script, which is very easy to learn and well optimized for game development. Scripts inherit the behaviors of the node type that they were attached to, in this case just a normal node. Templates are provided for different node types to provide basic functionality. The template checkbox is on by default, so let's take a look at what the default template for a node script has in it. We are creating a new script, not using one that is built into the engine. We can give the script a name, which will be recommended by the engine, matching the name of the node it is being attached to. It is conventional to use snake case when naming scripts, like the input actions, lowercase separated with underscores. Click the Create button to create the script, and the editor will automatically switch to Script View to edit it. You can switch back to 3D View anytime by clicking on the 3D button at the top of the editor. Likewise, switch to the Script View by clicking on Script. The top line specifies the node type that this script can be attached to, which is node. The keyword extends allows this script to inherit the properties and behaviors of a node, so we can use them in this script. Functions are behaviors that the script will run on the node it is attached to. Our script template starts off with 2 functions, ready and process. Gray text, starting with an octothorpe, are comments. Text that exists only for our benefit as the developer to explain the script in plain language. The comments tell us that the ready function is automatically called when the node enters the scene tree for the first time. This is not when we create the node in the editor, but when we press the Run Current Scene button. The simulation will build the scene tree, and when the player node is added to the scene tree and is ready, then it will call this behavior. The process function is called every frame, which with the default project settings is 60 frames per second. This function has a parameter named delta, which is the amount of time that has elapsed since the previous frame in seconds. This variable is represented as a floating point number, a number with decimal points. We can specify the type of any variable with a colon followed by the type name. Since Godot script is loosely typed, this is optional, but specifying a type will improve the efficiency of the engine and reduce the frequency of bugs. So it's recommended to always specify the type of your variables unless you need to allow multiple types. We can use the print command in our scripts to output basic text to the output console here at the bottom of the window. The print command takes a string as an argument, which is a sequence of characters contained within quotation marks. Let's print ready during the ready function and process during the process function. We can also use the plus operator to append strings together, allowing us to append the value of delta to the process string. But delta is a float, not a string, which is not allowed. We can cast the type of delta from a float to a string using the command str, passing delta as the argument in brackets. Run the current scene and stop it after a brief moment. In the output console, we can see that ready was printed once, followed by process 0.016, etc. many times, which is the frame rate of 1/60th of a second. Sometimes the number might be higher because that frame took slightly longer to process. So we can see that these behaviors are being called automatically by the engine. Let's remove these print statements and the entire ready function. Instead, we will want to check if the player is giving any input during the process function. To store this information, we need to declare a variable at the top of the script using the keyword var. Let's call it moveDirection. Preceding the name of the variable with an underscore marks it as private, meaning that only this script needs to be concerned with it. The type of our variable will be a vector2. A vector2 is a structure for holding two floats, named x and y. We've already been working with vector2 when resizing the plane mesh, and vector3s when editing the position or rotation of any 3D node. During the process function, we can set the value of moveDirection to the current state of the movement input actions we created earlier using the assignment operator, or equals sign. moveDirection equals input.getVector. Input is a singleton class, a built-in script that we can reference by its type, since there will always only be one instance of it. The period accesses variables or functions, which in this case are called methods because they belong to a class. The method we are calling is named getVector. GetVector accepts 4 strings as arguments, which are the names of the input actions that will be used to create a vector2, which will then be stored in the variable. A negative x value, which is left, will be subtracted from a positive x value, right, to calculate the value of x in the vector2. Likewise, a negative y value up will be subtracted from a positive y value down to calculate the value of y. This may seem reversed, but when looking at the input mappings, the up direction is listed as the negative side of the axis and down as the positive. Also, the camera looks in the negative z direction, so to move forward from the camera's perspective actually means to move backwards through 3D space. This is consistent with two-dimensional games, since the scene origin is at the top of the screen and positive values move down, not up. For now, we can just print the value of our variable to see what it is. Let's run the current scene and test it out. The output console is constantly printing 00 because no input is being given. If we press any of the WASD keys or tilt the left stick on our joypad, the values being printed will change. Left means the x value is negative, right positive. Down sets the y value to positive, which is toward the camera, and up negative, away from the camera. Closing the window, we can see a warning message. The value of delta is not being used by our process function. We can add an underscore to the front of delta to mark it so the engine knows that it can be ignored since we don't need it. We are now able to read player movement input from either keyboard or joypad. In this lesson, we will move a 3D object through our scene using that input. Let's start by removing all the meshes from our scene except the floor. And adding a new node to the game scene, a character body 3D node. This node comes with some built-in functionality for the physics of moving a character, but doesn't actually represent anything the player can see. So we should add a child node to the character body, a mesh instance 3D, which we can populate with a capsule mesh, with the intention of replacing this with an actual character later. The character body 3D is at the scene origin, on the floor, as is the mesh instance. If we consider the character's position to be between their feet, then the capsule should be moved up in relation to the character body. With the mesh instance 3D node selected, which should be childed to the character body, move the capsule up along the y-axis until it is on the floor, which should be 1 unit. Selecting the character body 3D node, if we move this node, the mesh instance will also move. Child nodes follow the position, rotation, and scale of their parents. There is a warning in the Scene tab stating that the character body needs a collision shape. This is another child node we need to add to the character body 3D node, a collision shape 3D node. It is not assumed by the Godot engine that collisions will happen when meshes collide. Instead, we can add an extra shape, usually one that is much more simple, to detect collisions in order to make the calculations more efficient. Much like the mesh instance 3D node needs a mesh resource, the collision shape 3D node requires a shape resource. We'll use the same capsule shape and move it up 1 unit to be in the same position as the mesh. This is now a branch of nodes that all relate to our character specifically and have nothing to do with the overall game scene. Right-clicking on the character body 3D node, select Save Branch as Scene, and give this scene a name. You can name this scene the name of the character, or just leave it as character for now. The child nodes in the scene tree are now hidden, and the character node has a clapperboard icon. If we click on the clapperboard, the character scene is opened up for editing. A new tab is opened in the editor for our new scene, and we can switch between the game scene or character scene by clicking on the tabs. The character is now a separate scene from the game scene that we can edit in isolation. Any changes we make to this scene will alter any instances of it in other scenes. Just like our player node has a player script, the character node also needs a character script to tell it how to behave. So attaching a new script to the root node of our character, this new script will inherit from character body 3D. We can use the basic template for this node type and click Create to open the new script. There are a few differences to this template. The character has a speed and jump velocity stored as constants. Constants are similar to variables but more efficient for values that never change. A gravitational force is being read from the project settings. Instead of the process function, there is a physics process function. By default, both the process and physics process run at 60 times per second. But in games with lots of complex physics bodies, the physics process framerate can be reduced to improve efficiency without sacrificing graphical updates or response time. So anything to do with velocity or force calculations are done in the physics process function to keep them separate. During the physics process function, if the character is not on the floor, then gravity times delta is being subtracted from their vertical velocity. If the player presses the UI accept action, a built-in input action assigned to the spacebar, then the character will jump. This template is also using similar code to read the movement input from the arrow keys. The input is then converted into a vector 3 by adding a 0 for the y value and using the vertical y movement for the z axis, converting up and down inputs on the keyboard or controller into forward or backward movement. This is then multiplied by the node's basis, which is a structure of 3 vector 3's pointing right, up, and forward. These are the same 3 colored arrows that are displayed in the editor when we select any 3D node. However, these arrows are in global space. If we rotate the character body, the arrows remain the same. The node's basis vectors are displayed if we switch to local space by clicking on this toggle or pressing the T shortcut key. As the node rotates, its basis vectors, or its local interpretations of right, up, and forward, will also rotate. These are the directional vectors that are being used to determine the direction the character will move when input is given. The direction is then normalized, meaning regardless of any rotation or partial tilt of the left stick, the length of the directional vector will become 1, resulting in the character always moving at a constant speed. This is shorthand for if the direction is not 0. Then move the character along the x and z axes by direction multiplied by speed. If the direction is 0, then move their velocity towards 0 at a rate of speed. Finally, the move and slide method is called to apply their velocity and external forces for the duration of delta to figure out where the character should be this frame. If we try to run this scene, nothing is drawn, because this is the character scene which has no camera or lighting. So switch to the game scene and run this one to test the game. The character immediately falls through the floor. This is because the floor doesn't have any collision. Let's add a static body 3D node to the scene. A body is a general term for any object which is affected by physics or collisions. Static means that it is unchanging, or in this context, that it will not move either from physics like gravity or from collisions with other bodies like our character. The floor mesh instance should be a child of this static body node, as it is the visual component of it. Then we need to add a collision shape 3D node to give the floor a shape with which it will collide with other bodies. This shape will be a box, and expanding the box shape resource, we can give it a length and width matching the floor, -5 meters in both length and width, and a height of 0. We can rename the nodes to reflect this new arrangement, so the static body 3D node is the floor, and the mesh instance 3D is a child using its default name. Now when we run the current scene, the character's collision shape will collide with the floor's collision shape, stopping them from falling. The floor will not react to the collision because it is static. Pressing the arrow keys will move the character body 3D node, and pressing the spacebar will jump. Back in the character script, the comments tell us that as good practice, we should replace the built-in UI actions with custom gameplay actions, which we already have. So we can comment these two lines, pressing Ctrl K or Command K. But the direction variable is being declared here inside the physics process function. This is called the scope of the variable. It is declared inside this function and therefore only exists inside this function. Like we did with the player script, we can declare this direction variable at the top of the script outside the physics process to expand its scope to the entire script. We'll set it to be private by preceding it with an underscore, and set its type to be vector3, a structure containing 3 floats for x, y, and z. And also edit the name of the variable inside the physics process to match. To move the character, let's write a new function in our script named move, which will accept a parameter called direction of type vector3. This direction parameter is different from our direction variable since this one doesn't have an underscore. And its purpose will be to store the value that was passed into this move function, assigning it with the assignment operator. The name of this function, move, does not have an underscore, marking it as public, which means that it is meant to be accessible to other scripts. Our player script will call this method to move the character based on the move direction that was received. We can switch between scripts by clicking on them in the list of scripts to the left of the script view. Switching to the player script, we can add a new variable to hold the character the player is controlling. This is a private variable underscore character of type character body 3D. Adding @export to the front of the variable declaration will allow it to be accessed by other parts of the Godot editor, namely the Inspector tab. In the game scene, if we select the player node, the character variable is listed in the inspector and we can assign its value. Since we specified the type of the variable to be character body 3D, only nodes of that type, or nodes that inherit from that type, can be assigned. Assign the character node to be the value of the character variable in the player node script, either by clicking on Assign and selecting it from the list, or clicking and dragging the node into the field. Instead of printing the value of move direction, we want to call character.move and pass the move direction as an argument. But the type of move direction is a vector 2, and the type of the parameter expected by the character.move is a vector 3. Even if these were the same type, this would not be the correct direction to move the player, since the direction that we expect the character to move is dependent on the camera's perspective. So let's add another exported variable for the camera. Then assign its value. We'll rename move direction to input direction and create another variable for move direction of type vector3. How do we convert the two-dimensional input direction into a three-dimensional move direction based on the camera's perspective? We multiply the camera's basis by the input direction similar to the way it was done in the template code, but we'll do it a little bit better. First, take the camera's right direction, its red arrow, which we can access with camera.basis.x, and multiply by input direction.x. If the player presses right, they will move along the camera's right direction, and if they press left, then input direction.x is negative, and right multiplied by a negative number will go left instead. Then add, using the plus equals operator, the camera's forward direction, its blue arrow, camera.basis.z, multiplied by input direction.y, converting the vertical input into movement along the camera's forward and backward directions. But the camera is currently rotated since it's looking down. So if the player moves forward, they will be moving slightly down into the ground, moving slower than they would left or right. And moving backward, they will actually be trying to move up into the air to move closer to the camera. Multiplying the basis vector by vector 3, 1, 0, 1 will remove any y component, flattening it onto the xz plane. We then need to normalize the flattened vector 3 so it will always have a length of 1 and not affect the player's movement speed. This will remove any effect of x or z rotation on these directions, but the camera's y rotation will still alter the player controls. Now when we run the current scene, the player script is checking for input every frame. If we give it input, then it will check the camera's right and forward directions, flatten them onto the xz plane, normalize them, and tell the character what direction to move based on the input. Then the character's physics process will move them in that direction. Moving the character using the camera's flattened basis vectors allows the player to maintain control of the character from any camera angle, and even while the camera is moving, we're also being controlled by the player at the same time since the movement direction is calculated dynamically every frame. Separating the player inputs from the character is also a more flexible structure since the character the player is controlling can easily be changed. And the script telling the character where to move could easily be controlled with game logic instead of the player input. We now have the player able to move a capsule through our scene. In this lesson, we'll replace the capsule with the character model. Let's start by downloading an asset pack from itch.io. For this course, I'm using the free version of KKit's character pack, Adventurers. Clicking on Download Now, you'll be prompted to pay, but you can click on No Thanks, just take me to the downloads. Or optionally choose to support the artist by giving any amount of money you feel is appropriate. There are also paid versions of these asset packs which include more content, so I recommend trying them out for free and paying for the extra versions if you like their work. Then click on Download to download the assets. While waiting for the download to complete, let's go back to the asset page and take a look at what is included in this asset pack. There are 4 characters, all with a variety of weapons and accessories, and each character is animated with a wide variety of animations for us to use in a consistent format. The models are efficient for use in mobile games and are compatible with the Godot engine. These assets are free for personal or commercial use under a Creative Commons Zero license. Be sure to check the licensing for assets you download before using them in your projects. In some cases, attribution may be required, or use in commercial projects may be forbidden entirely. When the download is complete, extract the contents of the zipped folder somewhere on your hard drive. Then open the folder to see what's in it. We want to use the characters, and the models are available in 2 different formats. For this course, I'll be using the GLTF files. Importing the assets into Godot is as simple as clicking and dragging them into the editor window. Our resource folder is starting to look a bit messy, so let's organize it. Right-click on the root resource folder and create a new folder. Let's name this folder Imported Assets. Then create another folder inside that one named Characters. Group select and drag the imported character assets into this new folder. We can also create a new folder in the root resource folder for holding scripts, and another for scenes. The scripts have a cog icon and the extension of .gd, while scenes have the clapperboard icon and their extension is .tscn. You can organize your resources however makes sense to you and best accommodates your workflow. Before we can work with the imported assets, we need to edit some import settings. Select any of the character.glb files in the File System tab. Then switch the dock that is currently displaying the Scene tab to the Import tab. Here we can edit how the Godot editor interprets the files and generates the imported assets. Most of these settings are fine for our purposes. First, let's add a root type of character body 3D. By default, the character will have been imported as a node 3D, but we want our character's root node to be a character body 3D to be compatible with our character script. If we change any of the settings, they will not be updated unless we re-import the asset. Next, click on the Advanced button. The Advanced Import Settings window opens, and we can see a preview of what the imported asset will look like. You can zoom in and out with the mouse wheel or click and drag to rotate the model to get a better view. To the left is the scene tree that will be generated by this asset, including a skeleton, bones, meshes, and an animation player with all the animations. Before we can work with this character model, we need to allow certain animations to loop. Let's start with the idle animation. With the idle animation selected, we can preview what it will look like with the play button at the bottom of the window. But it only plays once and then stops, which is exactly the problem. On the right side, we can change the import settings for the animation, changing loop mode to linear. Now when we hit play, when the animation finishes, it will return to the start and play again. Ping pong will instead play the animation backward to return to the start and forward again after that. Let's set it to linear. Then repeat for any animations in this list that contains the word idle, walking, or running. While not covered in this course, you may also want to allow looping for shooting, spinning, blocking, and spellcasting too. When you're done, click on the Re-import button to re-import the assets with the updated animation settings. You will need to repeat this process for the other characters too before being able to use them. Switch to the character scene. Click and drag the character asset onto the root node of the character scene to add it to the scene tree. Let's turn on preview lighting so we can see our imported character better, and delete the mesh instance node drawing the capsule mesh. The Barbarian node is just one node, not the big tree of nodes we saw in the import settings, and it has the clapperboard icon, implying that this is an instance of another scene. Like we created the character scene from the game scene, we can do that in reverse. Right-clicking on the Barbarian and selecting Make Local. This will break the link this node has with the imported asset and make it a unique version that only exists in this scene. And now we can see all of its child nodes. The animations are contained within the animation player node. Let's collapse the rig node for now to hide most of it. Next, we want the Barbarian to be the root node of this scene. We can right-click on it again and select Make Scene Root to organize the scene tree so that this becomes the new scene root node. Next, let's click and drag the collision shape 3D node to reparent it to the Barbarian node, making this the collision shape for the Barbarian. And delete the original character body 3D node since it is now redundant. However, we still need a character script attached to the root node. We can also add this by clicking and dragging it onto the root node. Our scene tree still looks the same as it was before, only the Mesh Instance 3D node is now replaced with the character rig, and there is an animation player node. Our character appears to be holding far too many items in their hands. Expand the rig node to view its children. We can hide any of the items being held in the character's hands by clicking on the eye icon beside them. We can also hide the character's hat and cape for any of the characters other than the rogue. The rogue has an entirely different model for when their hood is up, since the hair is also removed. Depending on the version of Godot or the assets you're using, there may be a red X icon showing that there is a problem with this asset. Selecting it and looking in the import settings, we can change the GLTF naming version to Godot 4.1 or earlier and re-import the asset to fix this issue. When you're done, collapse the rig once more. If we save the character scene from the scene menu or pressing Ctrl S or Command S, then switch to the game scene, we can see that the character in our game scene has been updated. And running this scene, we can move the character around just as before, but they are awkwardly moving around in the T-pose. We now have the character model imported into our project. In this lesson, we'll animate the character to walk around our scene. Let's start by moving the camera back a bit since the character is larger than the capsule was. The character movements are very rigid. The character is either moving at full speed or not at all. This doesn't feel very good and isn't how anything actually moves. There should be acceleration up to a maximum speed and deceleration before stopping. Opening up the script, we can see that the character's speed is declared as a constant. Let's instead declare some exported private variables to define how our character moves, starting with their walking speed, measured in units per second, which is best represented as a float. We can give variables a default value using the assignment operator in the same line when they're declared. I'll set it to 1. We also want acceleration and deceleration values measured in units per second squared, also with float types. Consider how quickly you would switch from standing idle to walking at full speed. About half of a second sounds reasonable, which is an acceleration of double the walking speed. And also how quickly you would come to a complete stop when walking at full speed. This is usually faster than acceleration, so I'll make it 4. Selecting the Barbarian's root node, we can see the exported variables available to be edited in the Inspector tab. Editing these numbers will overwrite the default values provided in the script, but pressing the reset button will return them to their default values. This allows us to easily experiment with different values and also provides the possibility of different characters having different movement speeds. To make things easier, we can separate the character's velocity on the XZ plane from their velocity along the Y-axis, allowing us to isolate adjustments in movement velocity from things like jumping and gravity. So let's declare another private variable, XZ velocity, of type vector3. At the start of the physics process, we can set the value of XZ velocity to be a new vector3, copying the character's velocity on the X and Z axes, while setting the Y value to 0. We can then make our adjustments to the character's XZ velocity here without worrying about the impact of their Y velocity. Then at the end of the physics process, before move and slide, we can set the character's velocity to be the adjusted values for X and Z, but the same value as it was for Y. And this method will also have additional benefits later. Next, we will need to edit this block of code that moves the character. The if statement is dividing this into two cases: if the player is providing a movement direction or not. Instead of breaking the velocity down into X and Z components, since we removed the Y velocity, we can simply edit the XZ velocity directly here. If the player is providing a movement direction, we should assign XZ velocity to move toward direction multiplied by walking speed at a rate of acceleration times delta. This will take whatever their current velocity is along the XZ plane and move it toward their walking speed in the direction that the player wants to go at a rate of acceleration, since delta is the amount of time that has passed since the last frame, usually 1/60th of a second. It will adjust the acceleration to match the frame rate, resulting in the character accelerating and moving at the specified speeds regardless of what the game's frame rate is set to. Likewise, when no movement input is given, the character should decelerate to a velocity of 0 at a rate of deceleration multiplied by delta. We can delete the original speed constant now, since it is no longer used. Let's switch to the game scene and try moving the character now. Now the character accelerates up to a walking speed and decelerates more naturally. Back in the character scene, we can switch to 3D view so we can see the character. Select the animation player node and the animation tab will open at the bottom of the window. The animation currently being viewed is one-handed melee attack chop, and the character model has assumed the first frame of the animation. We can press the play button at the top of the animation tab to preview the animation. Expanding the animation tab and scrolling through the animation tracks, we can see that each bone is keyframed to produce a resulting animation. Use the zoom slider to adjust the amount of time displayed in the animation tab, and you can see each individual keyframe. Using the drop-down, we can select any of the animations that were imported, including idle. And previewing this animation, since we configured the import settings, the animation will loop. So the animation player node can play any of these animations, we just need to control which animation is playing. You can do this through a script, but the code would be very long and have to accommodate too many possibilities. So the best way to control which animation is playing is using another node we can add to our character scene, an animation tree. The animation tree needs to be told which animation player it is controlling. So clicking on the Assign field beside Anim Player, we can select the animation player node from the list. Next, we need to provide a resource for this node just like we did with the mesh instances and the collision shapes. This resource is called a state machine. Creating the state machine will open the animation tree tab at the bottom of the editor window. We can pan the viewport of this window by dragging with the mouse wheel pressed. The state machine will track what state the character is in and play the correct animation for that state, or even blend multiple animations together. We simply need to tell the state machine what those states are, and also how and when the character will transition between states. For now, we will only have one state, which will blend the idle and walking animations together. If the character starts walking from idle, they shouldn't immediately transition from idle to walking, nor should they immediately transition back when they stop. Not to mention that the player will be able to tilt the left stick slightly to move slower if they want to. So we need the idle and walking animations to blend together depending on the character's movement speed. This can be achieved with a blend space. Right-clicking on empty space, add a one-dimensional blend space to the state machine, and name it Locomotion. Then click on the Connect Nodes tool. Click and drag from Start to Locomotion, making this the default state where the character will start when we run the game. Switch back to Select and Move Nodes, then click on the pencil to edit the Locomotion blend space. A one-dimensional blend space has one axis, which is displayed horizontally ranging from -1 to +1, named Value. If we consider this to be the character's speed, we can rename it to Speed and set its minimum value to 0 and maximum value to 1. 1 in this case should be considered to be 100% of speed, not a speed of 1 unit per second. We can add animations to the blend space with the Create Points tool. Clicking over at 0, we can add the idle animation, and at 1, the walking animation. Click Set the blending position within the space, then click anywhere along the axis to see how the animation looks at that speed. You can also click and drag to see how changing the speed over time blends the animations together. Now all we need to do is have the character script tell the animation tree the character's speed. Nodes can communicate with each other easily by assigning them to variables. And we can do it all in one line of our script using @onReady at the start of the declaration. Let's call this variable _animation of type animation tree and assign it a value. Using the $, we can then specify a node path to access any node in the scene tree, starting from this node that the script is attached to. So if the node we are trying to access is a child of this one, we simply specify the node's name. Following a sequence of nodes can be done by separating the node names with a /. If the name of the node contains spaces, you can put the node path in quotation marks. If you're ever unsure about the node path, you can right-click on any node in the scene tree and select Copy Node Path. Then paste it as text. Our script now has a reference to the animation tree node. All we have to do is set the blend space position after our XZ velocity calculations. Using the variable, we can access the set method to set any property we want. The property we want to set is defined as a string, representing a path to the property, using the same format as the node path. We can use the suggestions to autofill this parameter, looking for our locomotion state's blend position. Like with the node path, selecting the animation tree and the scene tree, we can expand parameters, locomotion, and copy the property path then paste it as text. Then specify the value we want to set this property to. which will be a value between 0 and 1 representing the percentage of the character's maximum speed at which they are moving. Since the xz velocity is a vector, we can use the length method to know exactly how fast the character is moving along the xz plane. Then divide this by their walking speed to convert it into a number between 0 and 1. Let's see how this looks when we run the game scene. Now the character blends between the idle and walking animation relative to their speed along the xz plane, but they aren't rotating to match the direction that they're moving. Try experimenting with different values for the character's walking speed, acceleration, and deceleration to see how they feel. In this lesson, we'll rotate the character model to look in the direction they're walking. Starting in the character script, if the player is providing movement direction input, then we can simply tell this node to look at its current position plus the direction. This will rotate the character body 3D node so that its forward basis vector is pointing directly at these coordinates. Since we have restricted direction to the xz plane, this will result in only ever rotating the character about the y-axis to face the direction the player wants to move. But the rotation will be immediate and point the character in the opposite direction. Since Godot reverses the z-axis, we can correct this by simply changing the plus direction to minus direction. Also, if we have any nodes childed to the character in the game scene, like the camera for example, then it will also be moved and rotated, which isn't what we want. So this solution isn't going to be sufficient. In the character scene, we can see that all the visual components of the character are children of a node 3D named Rig. Selecting Rig in the scene tree, we can edit its transform, clicking and dragging the Y rotation slider handle to rotate the character model about the Y-axis. This way, the character model can be rotated independently of the character body 3D, so it won't affect any other children in the game scene. In the character script, much like we did with the animation tree, we can use @onReady to store a reference to the rig node in a private variable. Then when we add movement velocity to the character, we can also tell the rig to look at where it's going. The character now faces the direction they're moving without affecting other nodes, but the immediate rotation might not be what we're looking for. So let's make the character rotate a little bit each frame. We can define a character's rotation speed as an exported private variable and give it a default value. Game engines typically calculate rotations in radians, not degrees. If you're not familiar with radians, a complete circle of 360 degrees is pi times 2 radians. There's also another mathematical constant named tau, which is pi times 2. But if we consider the use case for this value, we are only concerned with how fast the character will rotate up to 180 degrees, otherwise they would simply rotate in the opposite direction. So we can define the exported variable's value as a multiple of pi, or how many half rotations the character can make in 1 second, which inverted will tell us how long the character will take to rotate halfway around. Alternatively, you can define your character's rotation speed in degrees and use the degree to radians function to convert it when the game starts. I'll use the pi method and say that my character should be able to turn around in half of a second, making the rotation speed pi times 2. In the physics process, if the character is giving movement input, we first need to figure out what angle we are rotating to. We'll call this the target angle. We can find our target angle using trigonometry. If target angle is theta, which in this case represents the y rotation of an object facing in the direction, we can find it using the inverse tangent function, a tan 2. This takes two float arguments, which are our direction.x and direction.z values. Now target angle holds the value we want to gradually move our y rotation to. Next, we need the difference between these two angles, expressed as a number between negative pi and positive pi, telling us how far we need to rotate and in which direction. Subtracting our current y rotation from target angle will provide the difference between the two angles. To ensure that the character will only ever rotate along the shortest path, we then wrap this result using the wrapf function, making sure that the result is always between the value of negative pi and positive pi. We now have all the magic numbers we need to rotate the character, but how do we use them? We can determine the direction of the rotation using a function called sine, passing the angle difference as the argument. This returns -1 if the number is negative, 0 if it is 0, and +1 if it is a positive number. If we multiply this by the character's rotation speed and delta, then we know how much they can rotate and in which direction in a single frame. Adding this to their y rotation will rotate the character, but will also overshoot the target angle. So adding a clamp function, we can restrain the value rotation speed times delta to only be between 0 and the absolute value of the angle difference. The absolute value is with the sign removed, so a negative number will become positive. Then multiplied by the sign to ensure the character rotates in the correct direction. This will stop the character from overshooting the rotation and stop at the target angle. To make this more efficient, since we are only using the target angle once in the calculation of the angle difference, we can copy and paste its calculation into the same line and have one less variable. And since this process is running 60 times per second, it should not be declaring any variables, so we'll move the variable declaration to the top of the script. Lastly, we need to remove the lookout line below since it is no longer relevant. Now the character rotates gradually to face the player's input direction, and we can alter how fast they rotate in the inspector. Next, let's add a run button that the player can hold down to move faster. Open the project settings and switch to the Input Map tab. Add a run action. I'll use the Shift key or left face button. In the player script, we can react to the individual button press events more efficiently than we did with the movement inputs using a different function, _input. This function is only called during frames when there is an input event happening. Instead of delta, the parameter for input is an input event, which is a structure containing information about what the event was that happened. Inside this function, we can then check this structure to see if the run button was pressed. If it was, we can tell the character to run. Likewise, we can also check if the run button was released. And if so, tell the character to walk. In the character script, we can add a running speed to go along with the walking speed. Then add another non-exported private variable called movement speed, with a default value of walking speed. All we have to do in the walk and run functions is set the value of movement speed to be the walking speed or running speed accordingly. Then use the movement speed in our velocity calculations. However, when determining the blend position for the character's locomotion animations, we will use the running speed. Selecting the character's animation tree, we can then edit the locomotion blend space. Now if we consider a speed value of 1 to be the character running at full speed, we can use the Select and Move Points tool to move our walk animation somewhere closer to the middle of the axis, and add another animation on the far right for our running animation, either by switching to the Create Points tool or right-clicking. At any value of speed, the blend space will blend together the nearest animation to the left and to the right, applying weights to the animation based on their proximity. Back in the game scene, before testing out running, we may want to give our character some more room. So selecting the floor, we can edit the size of the floor and all of its children quickly by increasing its scale. Now when we run the game scene, the character can not only walk around the scene, but also run around by holding down the run button. Depending on the values you use for acceleration versus deceleration, it may seem like the character slides around, struggling to redirect their momentum. If we take a look at the physics process, the if statement breaks this down into whether the player is providing movement input or not. We can break this down further to also account for if the player wants to move in the same direction as the character or not. To check if what direction the player wants to go is similar to the direction the character is already moving, we can use some vector math. A dot product is a way of multiplying two vectors together that will result in a number representing how similar or different those vectors are. The dot product of two vectors both pointing in the same direction will be 1, and opposite directions -1. If the two vectors form a right angle, they are perpendicular, then their dot product will be 0. So we can check if the result of the dot product is greater than or equal to 0 to know if the character should be accelerating in the desired direction, since the player wants to move in more or less a similar direction to where the character is already moving. Otherwise, the dot product is negative, which means that the player is trying to move more or less in the opposite direction, so we should tell the character to decelerate, not accelerate. Now the character's deceleration can be applied when the player suddenly changes direction. We now have the character rotating and running around our scene. In this lesson, we'll add jumping animations. Let's start by enabling shadows from our scene's sunlight. Select the Directional Light 3D node, expand the Shadows section, and turn on the Enable toggle if it isn't on already. This will give us a little bit more perspective of how high the character is jumping. In the character scene, if we select the Animation Player node, the Animation tab should open at the bottom of the window. You can also open it manually by clicking on Animation here. Looking through the list of animations, we can see that there are several different jumping animations. If we select any of these animations, they will not play. This is because the animation tree is in full control right now. Select the animation tree and click the Active toggle to disable it while we explore the jump animations. Switching back to the animation player, open the Jump Full Short or Long animation and hit play. These animations aren't very flexible. We want our jumps to be more dynamic. Opening the Jump Start animation, we can see that this animation is what should happen when the player presses the jump button. Zoom in so you can see the animation keyframes. Since there are 30 frames per second, they are spaced 0.0333 seconds apart. We can set the snap to this value to allow us to scrub to each individual frame using the timeline. If we switch our preview to orthogonal left or right view, and zoom in on the character's feet, note that the character's feet remain on the ground for a whole 0.3 seconds of the animation. This is important since if we add velocity to the character at the start of the animation, it will look wrong. This is then followed by the jump idle animation, which should loop until the character touches the ground. Which should then lead to the jump land animation. Breaking these animations down like this allows the jump to be of any duration and still look good to the player. Also note that the final frame of the jump start animation is identical to the first frame of the jump idle animation. This is also true about the final frame of the jump idle and the first frame of jump land, but it's less important since the moment when the character lands could happen at any time. Selecting the animation tree node, we can turn it back on in the inspector and then take a look at the state machine. We can add the 3 jump animations to the state machine. I like to put them above the locomotion blend space, arranged in the same sequence left to right as they will be used. Add a connection from jump start to jump idle, then look in the inspector panel. These are the properties of the transition between states. We want these 2 animations to play in direct sequence, since the last and first frame are identical. So when the jump start animation is complete, just immediately switch to jump idle. Expanding the switch section, we can set the switch mode to at end, and the arrow icon in the state machine will change to indicate that this transition will happen at the end of the animation. Adding the transition from jump idle to jump land, we want this transition to happen immediately when the character touches the ground, meaning we won't know exactly what frame jump idle is in when this happens. To avoid awkward twitching, we can crossfade the 2 animations together for a brief window, like 1/10 of a second, just long enough for the change to not be immediate. As for when the switch happens, we want it to be immediate, but under a specific condition, when the character touches the ground. Expanding the advanced section, we can write any condition or combination of conditions we want in the expression text area to control when this transition will happen. Like in the character script, we can use the character body 3D node's built-in method isOnFloor to check if the character is touching the ground. When this becomes true, the transition will start, crossfading from jump idle to jump land for 1/10 of a second, then playing the remainder of jump land. However, to use this feature, we need to reselect the animation tree node and change its advanced expression base node property. This is the node that the advanced expression will be called on, and we want to use the character body 3D node for this to check the value of is on floor. Next, add a transition from jump land to locomotion. We will want to allow this animation to play in its entirety before transitioning back to locomotion, so its switch mode should be at end. While the final frame of jump land is the same as the first frame of idle, if the character lands while in motion, then we don't want to immediately switch from jump land to walking or running. So we can add a crossfade to this transition as well to blend it more smoothly. Adding a transition from locomotion to jump, this will be triggered by the player pressing a button. Expand the advanced section and change the advanced mode from auto to enabled. This turns the green arrow gray in the state machine since the transition is no longer automatic. This will allow us to manually trigger this transition through our character script later. Since we don't know what the locomotion blend space is doing at any random moment when the player presses the jump button, adding a brief crossfade to this animation will help smooth the transition too. Lastly, the jump idle and jump land animations could also be useful for if the player walks off of a ledge instead of jumping. So adding a transition directly from locomotion to jump idle will accommodate this case. We can set the advance expression for this transition to be if the character is not on the floor, and crossfading from locomotion to jump idle to smooth the transition. But what if the conditions for transitioning from locomotion to jump start or jump idle are both true at the same time? The character has left the floor and the player pressed the jump button this frame. If you want to control which transition takes priority in this case, you can select each transition and set their priority setting. The tooltip tells us that lower numbers are given priority when multiple transitions are possible. I'll give priority to jump start in this case by setting its transition priority to 0. We can preview how these animations, transitions, and crossfades will look by clicking on the play button on any state to force the state machine into that state. Note that this character is floating in empty space and is therefore not on the floor. Our character script is still using the basic template code to make the character jump. We should update this to match how we handle inputs for walking and running. Open the project settings and switching to the Input Map tab, we can add an action for jump. I'll use the spacebar and bottom face button on my controller as events for the jump action. Closing the project settings and opening the player script, we can add another condition to our if statement to check if the jump button was pressed. And if so, tell the character to jump. Switching over to the character script, we can add a public jump function. Before we can write the jump function, we need access to the state machine. Adding another variable declaration below the animation tree, starting with add-on ready, we'll get a reference to the state machine playback. Its type is animation node state machine playback, and we can access it from the animation tree using square brackets. Inside the square brackets, we can specify a path to what we're trying to access as a string. The thing we want to access is parameters/playback. Like before, if we select the animation tree node, we can see the playback resource listed here. Hovering over its name gives us the property path, or we can right-click and copy its path and paste it as text. Now that we can access the state machine when the character is told to jump, the character is on the floor, then we can request that the state machine travel to the jump start state. Make sure that the name of the state matches exactly. Then also copy the line from below which applies the character's jump velocity, and remove these lines from the physics process altogether. If we test this out, the character will jump, but the animation and velocity are not in sync. Adding another separate private function named applyJumpVelocity, we can set the character's y velocity to the jump velocity, moving the character body upward. And make sure the script is saved before you proceed. Disable the animation tree for a moment. Then in the jump start animation, scrub to the frame when the character's feet leave the ground. Clicking on plus add track, we can add our own tracks to this animation. The track type we want to add is a call method track. Next, select the node we want to call a method on, which is the character body 3D node. Scroll down to the bottom to find our newly added track, and right-click on that track where the scrubbed line intersects it. Then select Insert Key. We can call any method from our character script or any of the inherited methods from the character body 3D node itself. The method we want to call is to apply the jump velocity to our character. Remember to reactivate the animation tree before testing. Now when the player presses the jump button, the character will start the jump animation and wait until their feet actually leave the ground before moving upward. In some games, you may want the character to jump more responsively, and in that case it is important to use animations where the character's feet leave the ground at the start of the animation. We now have the characters jumping and falling animated. In this lesson, we'll improve the jumping and falling mechanics. Testing out the jump, there are a few problems. It's slow and floaty, the player has just as much control over the character in the air as they do on the ground, and we can't change the jump height in any way. If we look in the character script, the jump velocity is defined as a constant. We can also see that the force of gravity is being retrieved from the project settings. If we open the project settings, we can follow this string to find the gravity settings under Physics, 3D, Default Gravity. The direction of gravity is also editable here. Let's increase the gravity so the character feels heavier. I'll multiply it by 2. Note that this change will affect everything in the entire project that is subject to gravity. If you only want to affect the character's gravity, we can instead do that in the character script. In the game scene, switch to 3D view. In my mind, it doesn't really make sense to define a jump velocity. Instead, I like to think of how high I want the character to be able to jump. We can quickly and easily create basic geometry in our scene using a node type called a CSG, or Constructive Solid Geometry. Let's add a CSG box. Move it to the side and rest it cleanly on the floor. Add collision to the box by clicking on the collision toggle in the inspector. We can resize the box by entering values into the inspector or clicking and dragging the red dots in the preview. Resize the box until it represents the maximum height you would like your character to be able to jump onto. We can see exactly how tall the box is with its Y value in the inspector. But make sure that the bottom of the box is on the floor. Its transform position Y value should be half of its height. Duplicate this box either by right-clicking on it and selecting Duplicate, or using the shortcut Ctrl-D or Command-D. Place the duplicate next to the other box. Make this box taller than the previous one and have it represent a height that the character should not be able to jump onto. In the character script, like we have defined a bunch of variables to customize how the character moves, we can do the same thing with how the character jumps. Let's export a private variable named jumpHeight as a float and give it a default value somewhere in between the heights of the two boxes we just made. This will allow the character to jump onto the first box but not the second. Then add a private variable, not exported, to hold the actual jump velocity that is required to reach that jump height. We now have two completely separate categories of variables in our script, one for controlling how the character moves and another for controlling how the character jumps. We can add another line above these to further emphasize their distinction, @ExportCategory, then provide a string name for the category. I'll call these locomotion variables, and the ones below jumping variables. This not only provides us more information here in the script, but also separates them in the inspector. I'll also move direction into the locomotion category and gravity into the jumping category. And mark it as private with an underscore. If you want your character to experience a different force of gravity from other objects in your game, you can also export another variable, let's call it mass, and give it a default value of 1. This will act as a multiplier to the gravity being added to the character, so at 0.5 gravity would be reduced by half, or with a mass of 2, gravity would double. In the ready function, we can calculate the jump velocity using physics. The jump velocity required to reach the desired jump height is the square root of jump height multiplied by gravity, also multiplied by mass if you're using it, and multiplied by 2. Switch the jump velocity being added to the character's y velocity for this new variable, and we can now delete the constant since it is no longer being used. We also need to multiply gravity by mass in the physics process. Let's run the game scene and try jumping on our boxes. The character can jump high enough to reach the first box but not the second. Try experimenting with different values for jump height, gravity, or mass, and see how they change the feel of the character's jumping. What if the player doesn't want to jump at full height? Most games will have the character do a smaller jump tapping the button and a higher jump holding the button down. The character animation having a delay before actually jumping can really be beneficial for implementing this feature. Let's start by not defining a jump height, but both a max jump height and a min jump height. Which means we will also need a minimum and maximum jump velocity. And calculate both of these values in the ready function. We then need to scale the amount of velocity being added to the character based on the amount of time the button was held down. To measure time, there's a convenient node type we can add to our character. A timer node. Let's name this jump hold timer. And grab a reference to the timer node during the ready phase the same way we did with the other nodes. Since the name of the node contains spaces, the path is enclosed in quotation marks. Splitting the jump into two separate functions, let's call the first one start jump. When the jump button is pressed, we can start the timer. Then when the jump button is released, we can set its paused property to true, which means that when we start it, we will also have to set its paused property to false. So we'll need to edit the player's script to call start jump when the button is pressed, and complete jump when the button is released. In the inspector, we can see that the timer is set to count down from 1 second, which is longer than 0.3 seconds, so that's fine. But we need to check the one-shot toggle so the timer will only count down once and not reset itself every time it completes. When the jump velocity is actually added to the character, we can pause the timer if it hasn't been paused already, in case the player is still holding down the jump button. We can start by adding the minimum jump velocity, then also add the difference between the maximum and minimum velocity, multiplied by 1 minus the time remaining on the timer. Divided by the maximum amount of time possible, which we determined from the animation is 0.3 seconds. We never want this to be above 0.3 seconds, so we can apply the min function to cap it at 0.3. So if the player presses and releases the button within a single frame, this will be near 0, and the result will be minimum jump velocity. If the player holds down the button the whole 0.3 seconds, this will be 0.3 divided by 0.3, which is 1, and the result will be the maximum jump velocity. And any amount of time in between will scale linearly between the two results. Let's try it out by running the game scene. Tapping the jump button, the character jumps up to a height of 1.5 units, and holding down the button, they jump up to 2.5 units. Holding down the button for different durations produces jumps of different heights. Next, let's add more exported variables to our jumping category. Air control and air brakes. These are multipliers to acceleration and deceleration respectively, which will reduce the amount of control the player has over the character in midair without eliminating it entirely. 0.5 is a good place to start for their default value. You will need to thoroughly test to determine how you want the character to feel in your game. In the physics process, the first block of code rotates the character rig to face the desired direction. In most games, this will happen regardless of whether the character is on the ground or in the air. Next is adding the gravity, which only applies when the character is not on the floor. This block is moving the character, but it is doing it in a way that only makes sense when the character is on the floor, but applying it every frame regardless of whether they are on the floor or in midair. Then the locomotion animation blend position is being set, which again only applies when the character is on the floor. Applying XZ velocity and the move and slide method are universally applicable. So we can separate the parts of the physics process into general physics, ground physics, and air physics, writing a new function for ground and air physics, both private, and accepting a float parameter for delta. We can then cut and paste the gravity into the air physics function and the movement calculations into the ground physics function. Then in the physics process, if the character is on the floor, call ground physics. Otherwise, call air physics, passing delta as an argument to both. Our physics process is now much smaller and easier to understand, while the ground and air physics are separated from each other and easier to manage as well. So how do we apply air control and air brakes? Copy and paste the xz velocity calculations from the ground physics into the air physics. Then multiply anytime the player is trying to control the character in the air by air control. And anytime they are not trying to control the character in the air by air brakes. This is not the same as acceleration and deceleration in this case, since when trying to turn around in midair, the player is still trying to control the character. Applying the jump velocity 0.3 seconds after the jump animation starts will produce a large amount of coyote time to the character. If you don't want this, you can require that the character still be on the floor before adding the jump velocity with an if statement. Also, the movement speed initialization should be using add-on ready. Currently this is initializing movement speed to the default value of walking speed, but if we were to overwrite the default value of walking speed, it would not be assigned to movement speed. Use geometry blocks to build a small obstacle course for your character. How difficult is it to control the character's jumping? Experiment with different values until you get the feel you want for your game. We now have the character's jumping and falling mechanics feeling more realistic. In this lesson, we'll add camera controls to our game scene. Like we've done in previous lessons, it would be easy to simply child the camera to the player. The camera will follow the player around, but then rotating the camera around the player would be complicated. But if we just add another layer of separation, a node childed to the player with the camera then a grandchild, this becomes much more simple. The camera tilts and rotations that we expect from third-person controlled games can be achieved by only altering the rotation values of this intermediary node, either about the x or y axes. Rotating about the y-axis will rotate the camera around the character, like we expect from tilting the right stick horizontally. Rotating about the x-axis will tilt the camera up or down, what we expect from tilting the right stick vertically. Because the camera is a child of this node, it will match its rotation and stay focused on the character as well. We can adjust the camera's focal point, moving it from the character's feet up to their head by moving the node up along the y-axis. From here, we can also adjust the camera's horizontal offset property to further offset the camera along the x-axis to produce a shoulder camera effect. We can even control how far away the camera is from the character, and control that dynamically, by changing the node type. Right-click on the node and select Change Type, and search for Spring Arm 3D Node. We can also edit the name of the node to reflect its new type. With the camera as a child of the spring arm, we need to reset its transform so it has the same position and rotation of the spring arm. In the inspector, we can see the length of the spring is set to 1 meter. So the camera will always try to reposition itself to be 1 meter away from this node along its z-axis. Let's increase that distance to something higher like 5 meters. This spring arm node also has collision. So if there's a collision object between the origin of the spring arm and the camera, then the margin is how far from the collision the camera will be positioned. The camera will be positioned as close to the spring arm's length as it can get before a collision happens, compressing the spring. If the obstruction is removed, the spring will decompress and push the camera the full distance away. This is done with a ray cast, checking a single point along the spring arm's z-axis. But if we also specify a shape for the spring arm, we can give the collision volume, replacing the ray cast with a shape cast, requiring there to be more empty space before allowing the camera to move back to the full distance. If we make this shape a box, we can define its dimensions, and now the box will be used to detect how far along the spring arm the camera can go. To control the camera, we need to add more input mappings to the project settings. Open the project settings and switch to the Input Map tab. Add actions for look left, look right, look up, and look down. I'll use the arrow keys and right stick tilt for the events that will trigger each of these actions. In the player script, we already have a reference to the camera, but it isn't the camera we are actually going to control. We need to get a reference to the spring arm node. And set it in the inspector. In the process function, we can call a function we haven't written yet in a script we haven't even created yet and tell the spring arm to look in a direction. The direction to look we can get from input like we did here, input.getVector, with look left as the negative x, look right as the positive x, look up as the negative y, and look down as the positive y. Let's create the spring arm script. It will inherit from spring arm 3D. There is no template for spring arm 3D scripts, and the default node template isn't relevant. So let's uncheck the template toggle, allowing us to start from a blank script. I'll just name this spring arm and save it in the scripts folder. We already know that we need to write a public function named look, which will accept a direction parameter of type vector2 from the player script. We only need to then rotate this spring arm about the x-axis by direction.y and the y-axis by direction.x. But like everything that happens during a process function, it's happening 60 frames per second, and we want it to work independently of the frame rate, which means multiplying it by delta. But we don't have access to delta here, since this function doesn't have it as a parameter. We can add it to the list of parameters and pass it from the player script, or we can simply call a built-in method, getProcessDeltaTime, to retrieve it. Now the spring arm holding the camera will rotate with the right stick tilt. These rotations are happening at a speed of 1 radian per second. We can edit the speed of the rotations by exporting a private variable. Let's call it rotation speed. Then multiply this by direction and delta. If you want these rotations to have different speeds, you can export separate variables for them. While the Y rotation is typically allowed to loop endlessly around, the X rotation usually has limits. The controls will break if we allow the camera to tilt all the way to looking directly up or directly down. Since the camera's Z-axis flattened onto the XZ plane will become 0 or inversed. So we need to clamp the spring arm's X rotation to be between a minimum and maximum value. If the camera being flat with the horizon is a rotation of 0 radians, looking straight up or straight down is a rotation of pi over 2 radians, in either the positive or negative direction. So we only need to make sure that the absolute value is less than pi over 2. Clamping the X rotation between negative and positive pi over 3 is a quick and easy solution that still offers a wide range. We can also export these values and allow these limits to be tweaked. You could go further and use 2/5 of pi, or even use the degrees to radians function to convert 89 degrees to radians. So long as the camera can't go directly above or below the character. In the player script, we need to make some adjustments to our character controls. Since the camera is now a child of the spring arm, the camera is no longer rotating, at least not within local space. The spring arm is rotating and the camera remains stationary relative to it. We can get the camera's global basis vectors, which instead of being relative to the parent node, will be relative to the entire scene. Alternatively, we can use the basis vectors of the spring arm itself. and in this case we don't even need a reference to the camera at all. We now have the camera easily controlled by the player. In this lesson, we'll build a room for our character to run and jump around in. I've gone ahead and downloaded K-Kit's Dungeon Remastered Asset Pack from itch.io. Opening the Assets folder, if we look in the GLTF folder, there are a large number of models that we can easily import into Godot for our project. In Godot, let's first make a new folder inside the Imported Assets folder named Dungeon. With this new folder selected, importing the assets will place them in this folder. Just like with the characters, we will need to make some adjustments to the import settings of these assets. Let's start with Floor Dirt Large. Double-clicking on the asset or selecting Advanced from the Import Settings tab to open the Advanced Import Settings window. If we select the Mesh Instance 3D node, we can allow Godot to generate a collision shape for this asset automatically by checking the Physics toggle. A wire mesh of the collision shape is visible in the preview, and a new physics section is added with several options. Since the floor is part of the environment, we expect it to have collisions but not move as a result of those collisions or be affected by external forces like gravity. So its body type is static. There are a few different options to choose from for generating this collision shape, and we can see the current one was produced using Decompose Convex. This is fine for most objects in our game, but if we tilt the preview, we can see that the collision shape is noticeably far above the floor in certain parts. This would result in the character's feet not touching the floor, which wouldn't look very good. Selecting Simple Convex from the dropdown, this collision has fewer polygons than before and the same problem. The character's feet would not touch the floor in some places. Selecting Tri-Mesh, the collision shape will match the mesh instance exactly. Since these assets are low poly, this isn't really as much of a problem in terms of performance as it would be if this mesh were made of thousands of triangles. The character's collision shape will collide with these rocks, however. Depending on how you want your game to work, that might be a good or a bad thing. Just be aware of it. If you want to ignore the rocks entirely and just have a flat box for collision, then select Box for the collision shape. The box collision shape will not be automatically configured to match the size or shape of the mesh, but we can edit its dimensions and positioning here at the bottom of the panel. I'll select Tri-Mesh for this floor to demonstrate how the character's collision shape interacts with the rocks. Once your floor tile has the collision shape you prefer, click Re-Import to re-import the asset. Next, let's take a look at an object we might want to be more dynamic, like the Box Large asset. Like we did with the floor tile, we can select the Mesh Instance 3D node and add physics by clicking on the toggle. Since we want this to not only have collisions but also move around and be affected by external forces like gravity, its body type should be dynamic. Then select a collision shape for it. I'll switch this to Simple Convex. Some objects you might not want to bother with collisions or physics at all, like banners or other such decorative items. In those cases, there's no need to bother editing the import settings. Repeat this process for any assets you want to have physics applied to. There are a lot of assets in this asset pack. There's no need to do them all right now. You can always edit their import settings and add them to your game later if you want. We want to build a room with these assets, which we can do by clicking and dragging any asset into the scene tree to add it to the scene. But manually positioning each individual asset is tedious, not to mention that we may want our game to have different rooms. So like we have the character defined as its own separate scene, we want our game's levels to also be their own separate scenes. That way the game scene can load whichever level the player is currently playing in. Let's delete the floor and CSG boxes. We can instead replace them with a new node 3D to represent a level of our game. Let's call it Dungeon. Since the game scene is meant to play any level, and different levels are probably going to have different lighting, let's make the sunlight a child of the level node. Right-clicking on the Dungeon node, we can save it as its own scene, named Dungeon, saved in the Scenes folder. So all visual components of the game scene are actually contained within other scenes. The only things in our game scene should be the player input handler, a character, spring arm, and camera for the player to control, and the level. Then click on the clapperboard to open the dungeon scene. Here we can edit our dungeon separate from other stuff in the game scene like the camera or character. In the dungeon scene, we can add a new node type, a grid map node, which will allow us to quickly build out the level using the assets we imported. But the grid map requires a resource called a mesh library, which we have to generate first from the imported models. From the main menu, select Scene, New Scene, to create a new blank scene, and select 3D Scene in the Scene tab. This scene won't actually represent anything in the game, but will act as a collection of 3D models to use in the grid map. Clicking and dragging any 3D models you want in your grid map onto the scene's root node will add them to the collection. The models will all be at the scene origin, occupying the same space, which is fine. We can filter our resources to make the selection process easier using this field. Filtering for GLTF will show only the GLTF files. Group selecting the assets, they could be added to the mesh library much faster. Once all of the models you want to use are in the scene, save the scene not in the Scenes folder, but in the Imported Assets Dungeon folder. And name it Dungeon Mesh Library with the extension TSCN. Next, select Scene from the main menu, Export as Mesh Library. Let's save this in the same folder, call it Dungeon Mesh Library, this time with the extension .meshlib. Back in the dungeon scene, selecting the grid map node, we can assign our new mesh library in the inspector. We can drag the resource from the File System tab into the field, or click on the dropdown and select Quick Load. This will present a list of resources within the project of a compatible type. Selecting our newly created mesh library, we can see that the meshes have been populated into this selection grid. Selecting the floor tile asset, we can place a floor tile anywhere in the grid map by clicking. Positioning the tiles, they will snap to grid coordinates along the XZ plane. Expanding the cell section of the Inspector tab, we can edit the cell sizes that the floor tiles are snapping to. Since we know these tiles are 4 meters wide, let's set the X and Z cell size to 4. Now we can easily place a 3x3 grid of floor tiles by clicking. And delete them by right-clicking. All of these floor tiles are on floor 0. This is the cell coordinate along the y-axis. If we increase the floor, then the tiles will be placed 2 meters above. and likewise at floor -1, 2 meters below. And we can edit the floor height difference with the cell size Y value. If we want to add meshes to the mesh library later, we can return to the mesh library scene. This last wall asset needs to be re-imported with an earlier GLTF naming version. We can add more meshes to this scene. Then re-export it. Make sure the Merge with Existing checkbox is checked to update the existing mesh library to include the new meshes. Back in the dungeon scene, selecting the grid map, the new meshes are added to the selection grid. Not all of the meshes are 4 meters. Many are 2 meters or even 1 meter or smaller. Changing the grid dimensions to 1 meter, we can erase the current tiles since they are now overlapping. And instead select coordinates that are a few cells apart to redraw the floor tiles. But now a smaller mesh can be placed at coordinates every 1 meter instead of every 4 meters. While deciding on the location to place a mesh on the grid map, the WASD keys can also be used to rotate the mesh. With A rotating about the x-axis, S the y-axis, and D the z-axis. The W key will reset back to the default rotation. Create a basic dungeon scene from the assets and save it. If there are any objects you want to place not on exact grid coordinates, they can still be added to the scene separate from the grid map and positioned manually. Then return to the game scene. In the game scene, the dungeon floor is above the character, so let's move the character up above the floor. When we run the game scene, the character can collide with the floor, walls, and any other objects in the scene which had physics generated by the import settings. With these tools, you can build a wide variety of levels for your game quickly and easily, adding, removing, or changing things as needed. We now have a fully functional third-person character controller, allowing the player to control a fully animated character walking and jumping around in a 3D world.